Okay, welcome everyone. Glad you could all make it on this lovely Wednesday morning. My name is Jason Grillo. I'm the event director for Air Miners, and I'm glad to see so many people who have joined us so far. This event is about a deep dive into direct air capture technology, and something that's extremely relevant to our activities in air miners, in that direct air capture is one of many different important um, items in the carbon removal arsenal. To that end, we got some feedback that people were really interested in air miners, in the technology aspects of direct air capture. And to that end, we've got Dr. Jennifer Wilcox with us today. I'll send it to our moderator, Kristen Ellis, in a moment and introduce her. Point of logistics, if anyone should have any issues with messaging or with receiving untoward messages during the event today, please do email conference@airminers.org. I will put that into the chat so that we'll have it referenced, but like I said, don't believe that should be a problem, but if anything should come to pass that you'd like to report, conference@airminers.org. With that, I'm going to send this to Kristen Ellis and do a little introduction of Kristen, who is our MC for today. Kristen is a member of the Air Miners community, a biologist, community builder, open science enthusiast who believes that everyone's a stakeholder in technology. She has more than a decade of professional experience in a wide range of activities, including biotechnology, open space hardware, software products, open science, systems thinking, community building, startups, and strategic management. Currently, she's an entrepreneur in residence with Carbon 180, where she's working on carbon removal solutions at the intersection of synthetic biology, carbon tech, and more. Previously, she worked at Opentrons, a robotics-oriented Y Combinator-backed startup, and also has done work in clinical trials at MD Anderson Cancer Center in Houston, Texas. As mentioned earlier, she's active in several climate groups, including Sunrise Scientists and Open Air Collective, in addition to being a member of Air Miners. And she's also spoken internationally at several universities and scientific conferences on topics ranging from open tech ecosystems to community biology. So with that, I'm going to cede the floor to Kristen, and we will take things from there. Kristen.
Thanks, Jason. It's always weird hearing someone else talk about you like that, but that was a lovely introduction. Thank you so much. I'm very, very excited to be here moderating and listening to Jennifer Wilcox talk about her technology. Jennifer Wilcox is currently the James H. Manning Chair of Chemical Engineering at Worcester Polytechnic Institute. In addition, she's a senior fellow at World Resources Institute, and this fall she'll transition to a Presidential Distinguished Professorship of Chemical Engineering and Energy Policy at the University of Pennsylvania. She has a master's degree in physical chemistry and a doctorate in chemical engineering from the University of Arizona. Having grown up in rural Maine, she has a profound respect and appreciation of nature, which permeates her work. Her research takes aim at the nexus of energy and the environment, developing both mitigation and adaptation strategies to minimize negative climate impacts associated with society's dependence on fossil fuels. She has served on a number of committees, including the National Academy of Sciences and the American Physical Society, to assess carbon capture methods and impacts on the climate. She's the author of the first textbook on carbon capture, published in 2012, and she also gave a TED Talk on the main stage in April 2018 on direct air capture. I highly recommend both the book and the talk. And with that, I will turn it over to Jen so she can talk to us about direct air capture technology.
Thank you so much for having me here today, and thanks for everybody who's here for listening in and really just being interested in this topic. So let's get started. So this first plot that I wanted to show you to make sure we're all on the same page. This is an image that was generated for the United Nations Environmental Program. And what it shows is greenhouse gas emissions on the y-axis, and then the time frame on the x-axis. And what this is showing is what we need to do in order to prevent 2 degrees C warming by 2100. And what this is showing is that you see the business as usual trajectory here. And then to stay below 2 degrees C, you notice that we need to do some negative emissions. And so the new portfolio of mitigating climate change is not just about avoiding CO2 emissions, but it's also about actively removing the CO2 that's been accumulating in the atmosphere since the start of the Industrial Revolution. If this was 10 years ago, maybe we wouldn't have to think about direct removal of CO2 from the atmosphere. Maybe just avoiding carbon in the first place could have been enough, but we're no longer in that situation, and we're in a position of urgency when it comes to climate, and we need to do all of the above, which means deep decarbonization first and foremost, in addition to removal of CO2 from the atmosphere. I had the honor of being on a committee that in the National Academy of Sciences. We published a report in January 2019, and you can see the reference below. The group was a group of about 12 of us, and all in different areas of negative emissions technologies. So we approached it from all different types of approaches, which I'll talk about in the next slide. But one of the major conclusions from the study was the following. If the goals for climate and economic growth are to be achieved, negative emissions technologies will likely need to play a large role in mitigating climate change by removing globally 10 gigatons of CO2 per year by mid-century and 20 gigatons of CO2 per year by the century's end. These are very significant numbers. If we look at, on average, from the previous slide, on average, we emit globally somewhere around 40 gigatons. The terrestrial biosphere and the oceans naturally uptake about half of that, roughly. And so that remaining half of roughly 20 gigatons, we're just dumping in the atmosphere every year, and that's steadily accumulating in the atmosphere. So that deep decarbonization needs to be avoiding that significantly. And keep in mind that we only really start to touch the 410 roughly parts per million of CO2 in the concentration in the atmosphere. We only start to decrease that with negative emissions until we first avoid at least 20 gigatons of deep decarbonization every year. And so in order to meet climate goals and doing both, one of the major conclusions from our study was this. And so it's just deep decarbonization in addition to these significant reductions directly to CO2. These are the various approaches that we considered in the report, and the report's very long. It's 300 or 400 pages. You can access it online if you want. We went from looking at coastal blue carbon, which has a lot of co-benefits associated. So the impacts of doing coastal blue carbon may not be as significant as some of the other approaches, but the co-benefits are pretty spectacular. So you can kind of, if you look at the report, you can get more insight into what that is. Accelerated chemical weathering of rocks. And so there are rocks in the Earth's crust that naturally react with CO2 in the atmosphere. And now we're looking at engineering ways to accelerate that process, either by using mine tailings, industrial alkalinity. Reacting alkalinity with CO2 is one way to also remove CO2 from the atmosphere. Biomass energy with carbon capture and storage, specifically when we focused on this called BECCS. And when we focused on this in the Academy of Sciences report, we looked at forest management and looked at waste biomass that already exists in forests today, and maybe modifying that waste biomass through a process called, say, torrefaction, where you convert the biomass into a form that would mimic pulverized coal in an existing boiler today. So imagine retrofitting coal-fired boilers with biomass, pulverized biomass, and in that kind of a way, so you can keep that existing infrastructure and then retrofit the biomass energy facility with carbon capture. And this could be potentially a negative emissions technology. Planting trees, either planting trees in an area that had forests before and trying to, you know, bring that biodiversity in those forests back, or even planting trees in an area that didn't have a forest before, afforestation. Enhancing carbon storage in soils is another approach. So think about low tillage, advanced agricultural farming practices that help to maintain the carbon in the soils. So in our report, we talk about all of these. Now, an important distinction between some of these is like BECCS, and then what I'm really going to talk about in the next, say, 30, 35 minutes in a deep dive is direct air capture. But these two have a bridge, and the bridge is that they are not a negative emissions technology unless you permanently remove the CO2. So in both of these cases, we're drawing CO2 down from the atmosphere, and this is using chemicals to do that. In this way, we're using biomass, and then you know, extracting, you know, combusting the biomass and producing, say, electricity or energy from it. But in both of these cases, you have to do something with the CO2. So that thing that you choose to do, whether it's, if it's utilization and you convert it to a fuel, that CO2 is only going to be oxidized ultimately and put back in the atmosphere. So we say that that is at best neutral. You know, if all the energy flows that are going into that process are carbon zero, then that's at best neutral. If you convert it to, say, a fuel, or if you use it for a greenhouse, or if you for food and beverage, you're re-emitting the CO2 back in the atmosphere. And so for it to be negative emissions, to pull carbon dioxide out of the atmosphere and have it permanently be removed and not go back into that atmosphere in that accumulated pool, you really have to turn it into something where you have to inject it into a deep geologic formation. It could be a depleted oil and gas reservoir, it could be a saline aquifer, or you could actually turn it into a mineral. You know, so mineralization of CO2 is another possibility of reliable storage. And so that's an important distinction. So what is direct air capture? So using chemicals to remove CO2 from the atmosphere. I'm going to talk about kind of the leading technologies of doing this today. But I want to first start off thinking about, you know, in the air, it's roughly 400 ppm CO2 concentrations. From a coal-fired power plant, it's roughly 12% CO2 and mostly nitrogen and some oxygen and water vapor. And in natural gas electricity or a natural gas-fired power plant, that type of utility has anywhere from 3 to 5% CO2. So some of the pros of capturing CO2 from the atmosphere, it has the potential to be a negative emissions technology if it's coupled to something that permanently removes it. It's a method of dealing with difficult to avoid emissions. So that would be like the transportation sector is difficult to avoid. Some of the agricultural sectors are difficult. The industrial sectors, so cement production, iron and steel are difficult sectors. The other aspect is it doesn't require arable land. That doesn't mean it doesn't require land. It requires significant land. We'll talk about that later, but the key is that you're not competing for food when you build a direct air capture plant, like you might be when you're, say, planting biomass. Cons, the energy inputs are significant. We can start to see that just by seeing how dilute the CO2 is in air compared to point sources. And although more efficient than planting trees or a forest, the footprint is still, it's still large. And I always like to say direct air capture should not mitigate. If you don't have your microphone, or if you're not mute, please do that, because there's a lot of feedback from somebody.
Yeah.
Okay, so let's take a quick look at the energy. I am a chemical engineer by training, and so I appreciate the second law of thermodynamics. And in fact, I've had several conferences on this topic, and I made a shirt with the second law on it because it's the only thing that's really limiting what we can do. It tells us how good we can have a process. So you can calculate the minimum work of a separation process by combining the first and second laws of thermodynamics. And what that tells you is that if you know what your CO2 concentration is, say it's from the air or from a point source, and you know how much CO2 you want to separate. Maybe it's 50%, maybe it's 90%, and you know the purity of that CO2 in the end. And the reason the purity is important is because if you have to transport the CO2, to do that easily, you have to have it in a condensed phase. And to get it easily into a condensed phase, you have to compress it. And so high purity CO2 is more compressible than, say, low purity CO2. And so you have to spend the energy to do that. And so if you know that final purity, which if you're putting it in a pipeline or a truck, it's typically 99% plus, and you know the percent capture that you're trying to take out of the air, and you know the initial CO2 concentration, you can do this calculation. And this minimum work tells you the lowest, the lowest you can go. In a real process, and we'll talk about these, whether it's a solvent-based approach or a solid sorbent-based approach, you have pumps, you have fans, you have absorption columns, you have heat exchange. And in all of those types of processes, those are real systems, and each of those unit operations has an efficiency associated with it. The minimum work is just the minimum, and it's technology and process agnostic. It doesn't care. But the real work means that you've defined a process and you've outlined that. And the real work, because of those inefficiencies of each of those unit operations, the real work will always be more significantly larger and higher than the minimum work. And so that's what this is showing. And ultimately, we can compare direct air capture to point sources to just show that, sure, the real work is going to be higher, but even the minimum work, if you have a more dilute stream, the work that it takes to separate the CO2 out of that more dilute stream is always going to be higher than the more concentrated streams. In fact, we can kind of do a comparison and say, for the case of CO2 from a power plant versus, say, direct air capture, because the concentration of CO2 is so much more dilute in the atmosphere, it's about 3 times more energy in terms of just the minimum work to capture CO2 from the atmosphere compared to the exhaust stream of a power plant. And again, because the concentrations are so different, it's the contact area of the contactor of the direct air capture plant is 300 times the size of what the contactor area would be from a power plant exhaust. These numbers translate directly into the operating costs, because the operating costs correlate strongly with the energy it takes to do the separation. And then the contact area, the contactor is a very significant capital expense of a direct air capture plant. And so by comparison, this contactor area directly translates to the capital cost increase of doing this. And so just looking at this from a qualitative perspective, it's always going to be more expensive to capture CO2 from air than it would be from a point source. And that's why something like direct air capture should not be seen as a replacement for just avoiding CO2 in the first place. So before we get into what the contactors look like in a direct air capture plant, I wanted to quickly just show you typically what these absorption units look like. So this is what CO2 scrubbing looks like from a point source. So this is the Petronova project that's in Texas. And the way that this looks, as you can see, it's kind of tall and thin, and it's shown here in this picture. And what happens is what I call here, these are theoretical stages, but what you have is you have a liquid solvent that has a chemical in it, okay? And that chemical is typically like 30% by weight of the entire solution itself. And this inside of the column is filled with packing material. And so what you do is you pump the liquid solvent down through the absorption column. And the idea behind that is that you want the liquid to coat the packing material as evenly and distributed as possible. And you want just a thin layer of solvent over the packing material. And the point of that is that when you bubble your gas in through that liquid, and the gas is, say, in this case, it's coming from the exhaust of a coal-fired power plant. So when you bubble that gas through, maybe using a blower technology here, because it's a pretty high pressure drop to push that up. And so you bubble that gas in, and what you're wanting to do is every bubble of gas that's going in at the interface of the bubble and the liquid, you want to have contact so that the CO2 sees the chemical in solution, diffuses in, and chemically reacts. So that when you bubble out, you know, in the end, the gas that comes out is clean of CO2. And the solvent that you collect at the bottom of the column is saturated with CO2. And the whole point of the contacting material, the packing material and the solvent, is to really create a high surface area. So you get as much of that CO2 as possible to see the solvent and chemically react and leave the system and come out clean. Now, this technology was invented back in 1930. We know it pretty well. And this technology is based on a chemistry called amines. And amines are just nitrogen functional groups, and nitrogen likes to react with CO2. Amines are a pretty weak base, but because the concentration of CO2 in a flue gas is not as low as air, we can use weak bases to do it, and it works just fine. So now that I showed you is kind of a tall, thin tower, right? And one thing I just want to point out here too, by the way, is you could imagine the taller this tower, the cleaner this gas is coming out, right? Because with every stage, you get a little more CO2 out. So how do you get all the CO2 out? The only way to do it is to have an infinite column. And we would never do that because it would be way too expensive. And it's just not realistic. And so now let's look at direct air capture and why it looks so different. And so here, this is a very different design. In this case, what happens is you have still a packing material that goes inside here, and you still have that solvent, you know, that coats the packing material. You don't have blowers in this case because blowers take a lot of electricity, they're high power, but you have fans. Okay, so fans allow you to have what's called a lower pressure drop, and a lower pressure drop just means we have a thinner bed. And so what I spoke about before, very different, right? Tall and thin. They can be tall because the airflow coming out of your exhaust of your power plants, it's going pretty fast. But on average, in the atmosphere, you know, a lot of times we use an average, you know, air velocity of say 1.5 meters per second. And so you've got the air flowing in, it's being drawn in by the fans, but we don't want this bed to be too deep because it would require more fan power. And we don't want to spend a lot of energy, right? We want to minimize that because that's how we minimize costs. So by having a thinner bed also means we don't capture as much CO2. So from the power plant, we often design those systems to capture 90, maybe even higher than 90%. These are optimized to capture probably between 60 and 70%, depending on what the bed depth is. And so that gives you a little bit of an idea of the difference. The other piece is look at this contact area. It goes back to that minimum work slide that I showed you. In order to get the same capture of CO2, say per unit time, you know, as you would get from the point source capture, you really need to have a more significant contact area, on average 300 times if it's comparing, say, the exhaust of a coal-fired power plant to the atmosphere, 100 times if it's natural gas. So now we get into the two types of technologies that are kind of leading the way today for direct air capture. One is the solvents, and that's what I've mostly been talking about. This is some example of a metal packing material, but this metal packing material is what we use in Petronova. It's not necessarily the best material that you would want to use for direct air capture. It has a higher pressure drop than, say, plastic or PVC packing material, which is what Carbon Engineering is envisioning using and uses in their plant at Squamish, British Columbia. So it's PVC, lower pressure drop, maybe cheaper to make too. And so there's definitely differences between the materials that you would use for not just the differences in the design, but also differences in the packing material that you might use between point source capture versus direct air capture. So let's switch gears. This is solid sorbents. And so if you've ever looked inside your catalytic converter, it looks a lot like this. And so the catalytic converter in your automobile is this honeycomb structure. And you see these holes in it are on the order of about millimeters. Now, you could imagine that creates some surface area, but not nearly what you need. And so the walls of this honeycomb structure is coated with another type of material. And this is the expensive part. This is the cheap part. But the expensive part is what's called micro mesoporous materials, and those have very high surface area. Micro mesopores just mean that your pore sizes are on the order of, say, nanometers. And if you take a gram of that material, it has roughly the surface area of a football field. That's pretty amazing. As a chemical engineer, I get super excited by that because I think it's pretty phenomenal that in just a gram of material, you have surface area of a football field. And so imagine that football field, how much amine chemistry you could paint on that surface. A lot. So very different from this approach where our surface area is really maximized based upon the coating to the packing material. You see kind of the shape of the packing. Now it's like our surface area is so much more significant, right? And so we can use a weak base. The solvents use a very strong base. So they use a potassium hydroxide by 30 weight percent in their solution. They have to. In this case, we can actually go back to using weak base like amines. And so we decorate those micromesoporous materials with amines. And then what happens is, in this case, this is kind of going, in here, and that's the packing material. And it turns out that it's called adsorption because the CO2 is reacting with an amine on the surface of a solid substrate, where this one's called absorption because it's being absorbed, into the solution. So those are the two distinctions. And then this is a lot of information, a little too much, but if you go to chapter 5 of our National Academy of Sciences report that came out in January last year, you can see this. It's a complicated design. This is the solvent-based system, very similar to what carbon engineering has, where you have that air contactor with your strong acid, potassium hydroxide. And so the kinetics are very favorable. It's very selective to CO2. You have this potassium carbonate that you form in solution. And then you have another reaction. The other reaction is that you add to that solution calcium hydroxide. And the reason you do that is because what happens is the calcium has a preferred reaction with the CO2, and it crystallizes out of solution. And crystallization is a separation process very familiar to chemical engineers. And so the calcium will preferentially react with CO2 and form a carbonate. And it's literally just crystallizing out a solution. And then you need to filtrate that and separate that carbonate. And that's just a solid material. And so ultimately in the end, you get this very stable calcium carbonate. And how do you regenerate the material over and over again so that you can use it in a sustainable way? You have to heat the calcium carbonate. It looks very much like making cement. So you have to calcine it. And calcining calcium carbonate typically means heating it in a furnace to 900 degrees C. So it takes very high quality heat to do this process. And then the question is, with direct air capture, since climate is what we're really trying to, that's our audience, right? And so in doing that, what it means is you have to be very careful about all the energy flows going into your system. And so if you're heating something to 900 degrees C, you have to ask yourself, what is my fuel? If I'm using coal, nobody would do that. You end up putting more carbon back in the air than you capture. If you use natural gas and forgetting about leakage in the Permian Basin and that supply chain for a minute, if you just use natural gas without carbon capture on the natural gas, you end up kind of net removing half of what you intended to capture. And so you really have to think about the energy resource that you're coupling to the system. And so one way of doing this is the calcining that calcium carbonate at 900 degrees C in a furnace where the natural gas is fired with oxygen instead of air. And so if you fire the furnace with oxygen, then that means that you're really producing the combustion byproducts of CO2 and water vapor, and nitrogen's not there as an inert gas because you've just fired it in oxygen and not air. And so ultimately in the end, you have a very easy separation process because you just have CO2 and water vapor. And you have a condensing unit that can separate that very easily. So the key to this today is oxygen fired technology, which is exciting because that's also a key to making the cement industry lower carbon as well, because it looks very similar to this calcining process for the solvent technique. For the solid sorbents, very different. The air contactor looks pretty similar, as I showed before. But in terms of this, the heat quality is much different. And so instead of 900 degrees C heat, you can get away with, say, 100 degrees C heat. Again, it's a weaker base, right? You're able to use amines because you've kind of offset that weak base with having a significantly high surface area of your material. And so in the end, you know, you also have the contactor being the same unit as you're doing the desorption. So very different here, where you're having to kind of move your fluids and move your solids all around this different system. In this case, your air contactor becomes your desorption unit as well. And so you essentially capture your CO2, and then you add steam, and that steam goes through the channels, or maybe you have some heat exchange where you thermally drive off the CO2 that's absorbed. But there's also those channels that might have, say, oxygen, or maybe even a little bit of water vapor or nitrogen that are residing. So there's always a combination of thermal versus vacuum. It's called vacuum swing, so that you can, during the stage of desorption of CO2, you can pull a little bit of a vacuum on the system to pull some of the oxygen out and some of those other gases that reside in the pore spaces. And then you have finally a step where you pull the CO2, and then ultimately separate any water and have a condensing unit in the end. So to design a direct air capture plant, this goes back to one of my original slides, is how much energy it takes to do this. No matter which technology you choose, to capture 1 million tons of CO2 from the air requires a power plant, roughly 300 to 500 megawatts. And so it's very significant. Now, how does that power plant look? We think of power plants as like natural gas or something like this. It could be photovoltaics, it could be wind, preferably low carbon energy. But you just have to keep in mind that 80% of the energy is associated with thermal, and only 20% is electricity for like the fans and the pumps and the compression and things like that. And so both of these technologies are very thermally driven. It's not that one requires less energy than the other, it's that one requires lower quality heat than the other. And so the solid sorbent based approach is 100 degrees C and the other one is 900, but they're both very energy intensive processes. In our National Academy of Sciences report, we were asked to develop a research agenda for this field. And so in doing that for direct air capture, I like to look at, well, how does the CapEx look? So when we look at the costs and the capital costs of each of these processes, how does it break down? And it's a different story for each one. And so if you look at the solvent-based approach, you notice that a lot of, it's a split in terms of the capital cost. It's really the large pieces of equipment that you have to purchase in order to do this. Due to economies of scale, it makes sense for the solvent-based approach to build plants that are, say, on the order of 1 million tons of CO2 per year, because you have these large units like an oxy-fired calciner. And you also have, the contactor array is still also a significant part of the price. And then you have the other units that I talked about too, like say a pellet reactor or that method of filtration of the crystallization process. And then in terms of the solid sorbents, nearly 80% of the capital is associated with the micro-mesoporous materials. So those nitrogen functionalized materials that you need to actually do the chemistry. Those are expensive to make. It doesn't mean that we can't shrink this down, but I like to think about some of the work that I'm doing to try and help create the human capital that will make that happen. Some of the students in my group now are looking at supply chains associated with just traditional catalysts, zeolites, activated carbon. And the question is, if we're going to scale up to gigatons with direct air capture by mid-century, what does the supply chain look like for those materials compared to how we use them today? Is it 100 times? Is it 1%? And so that's some of the work that we're doing to just try and understand. Because if those chemical companies have figured out how to scale catalysts up and we figured out how to scale up activated carbon, then I have no doubt we can do it here too. We're just at the beginning stages, and this is the expensive piece. But the beauty of this kind of work tells us that and reveals that. And so that's where the R&D needs to go. So next piece I wanted to look at is a little bit of the land. And so looking at, thinking about this, so in 1966, the US invested about 0.5% of GDP in the Apollo program. If we look at that today, that's about $100 billion. And so knowing that direct air capture is just one of a portfolio of solutions, say that we invest 20%. And if we do that, if we invest 20%, and there's another caveat, suppose that we can get the cost of doing direct air capture down to $100 a ton. Now, there's a lot of studies out there that have a broad range of costs reported for direct air capture. I personally think that if we have increased deployment and learning by doing, that we could get costs down potentially this low. So let's just assume we could. So if we do that, that would mean, and we had this kind of investment, it would mean building 200 direct air capture plants, each capturing 1 million tons of CO2 per year. And so doing this would be equivalent of about 5% of our annual emissions. Another reason why there's no silver bullet, like we really need everything. Okay, so even all of this, that's what it gets us. And so what I wanted to do is give you an idea of what the amount of land that would be required to actually do this. So again, just focusing on the solvent-based approach here, suppose that we were to use natural gas and the natural gas was coupled to carbon capture and storage. And oh, by the way, suppose the supply chain of natural gas was leak tight. That's the only way that we could really make this feasible. And so if we, as one scenario, the second scenario is suppose that we don't touch any fossil fuels to power the plant. And remember that the scenario before was an oxygen-fired kiln. So you have to think of a new way to heat up that rock. And so one of the ways we thought about it is, well, what about a hydrogen-fired calcining? You could also think of using an electric kiln, like resistive heating, but we chose hydrogen-fired here. And so imagine too that all your electricity needs, that 20% was coming from solar. Imagine that you also had to do electrolysis. We're not talking about costs, keep in mind, we're really just talking about the land area here. And so this is, you know, I know I'm on the East Coast, but this is from a presentation I gave out in California. And so if we powered with natural gas and with CCS, 200 DAC plants would be about 1/6 the land area of San Francisco. If we chose to power with photovoltaics and hydrogen, it'd be 1/10 the area of California. And so the choice of energy resource is really important. And it would be nice to use low carbon energy too. It would be great, right? Because you really maximize the benefits, but we do have to be careful when we make those choices. And I'm not saying that one is better than the other. In some regions, you have this kind of land area to do that. In some regions, you may not, you know, and that's why it's important to, if we're using natural gas, to do it in a responsible way, either having carbon capture and making sure the supply chain is leak tight. But it just goes back to showing the energy density of fossil fuels versus, you know, renewables. So I don't have a whole lot of time left, but I have a few slides that I wanted to go through. This is a 3-paper series that was just published in the last couple of weeks from my group. I'm going to talk a little bit, just have a few slides associated with the direct air capture study that we did. But if some of you are interested, we also had part 1 that was on carbon capture costs and retrofits, the natural gas electricity sector, and another one that looked at opportunities for retrofitting for the industrial sector. We looked at all different industries. So in terms of the part 3, where we talked about direct air capture, what we wanted to do is say, how low could we get this? You know, how could we reduce the cost of direct air capture today? We specifically focused on the solid sorbent-based case because the requirement for the thermal energy was 100 degrees C. And so thinking about opportunities where there is thermal energy available at 100 degrees C, and somebody else has already invested in the development of the infrastructure. And so imagine the direct air capture is just piggybacking on that. And so we specifically coupled with geothermal. And so this would be existing geothermal or new geothermal power plants. In a geothermal power plant, you typically have a condensing unit to maximize the efficiency of the plant. And you could imagine if you can promise that the working fluid goes in the DAC plant at say 90 or 100 degrees C and comes out at 60 or 70, that's a pretty good condensing unit. And so one could imagine even a new build, the DAC plant replacing that. The other benefit is that you have a geothermal plant, and the other example is nuclear, but in each of these cases, in each of these power plants, you know, they're producing carbon neutral electricity. Imagine if they could produce negative or carbon negative electricity. And so coupling with direct air capture could be an interesting way to look at that. And so what we did is we also said, well, what about 45Q and how does that fit into this? And so in doing that, we had to estimate the costs of capturing the CO2, but then we also had to estimate the costs of transporting it to all of the opportunities that are out there, either dedicated storage or enhanced oil recovery. And so that's kind of what we've done here. And so we did a comparison of the geothermal, the nuclear, compared to a base case. And I think I'm going to skip to the map here. And so what this shows is the orange circles aren't wells today, but they could be opportunities or places where there's sedimentary basins where dedicated storage is possible. And then the open black circles are where there's enhanced oil recovery taking place today. And I have a couple of slides where I want to talk about enhanced oil recovery as well. And then the green are existing geothermal power plants. The size of the circle has to do with the flow of their working fluid, which would indicate how much direct air capture you could do there. And so that's the size of the direct air capture plant. The nuclear, what we're doing is working with the facility. We had 2 co-authors from Exelon on our study, where you work with a nuclear facility and you actually pay for 5% of their slipstream of their steam and use it for the regeneration of your material. And so those are in gray. And so when we look over at the costs, we have the costs of capturing, but we also have this net delivered. And so if you're trucking, for instance, the CO2, the truck has a carbon intensity associated with the transportation part. If you are using grid-based electricity in each of these states, then that's going to play a role in the net removed CO2 from the atmosphere. So these costs are really taking into account the life cycle of that process. And so we are able to, again, by piggybacking on these industries, we're able to say get down less than 300 and almost down into the low 200s for geologic storage, and which have more sites and more opportunities compared to, sorry, I have a cat here, compared to EOR, which are only in certain regions. So very briefly, I just have 2 more slides. The US market today, because again, you have to ask the question of what do you do with the CO2? The market for CO2 utilization today is about 80 million tons. The largest use sector is EOR, so using CO2 for enhanced oil recovery. There's policy incentives. There's the low carbon fuel standards, which also applies to direct air capture at about $200 a ton. There's also the federal tax credit, 45Q, which again, we applied in the previous work that I just showed for qualifying streams. There's emerging markets like construction and synthetic aggregates, which has the potential to scale to gigatons, and there's fuels. But remember, we have to be careful because that's at best neutral and not negative. And so I'll just mention the first CO2 EOR project was in 1972 in the Permian Basin. We have not had any leakage of CO2. There have not been accidents. We know how to do this. We've been doing it for a long time. The other aspect about CO2 I think a lot of people don't realize is that the CO2 is a tertiary method, which means that the projects have been recovering oil and gas through primary recovery, which just means drilling a well and recovering oil and gas. Secondary would mean pressurizing it, maybe by water flooding. Tertiary is when you inject the CO2 and at those temperature and pressures in the earth, it's miscible with the oil, changes the chemical properties and allows you to recover more out. And when you recover it out at the surface, and as the pressure changes, when you recover it, the CO2 comes, separates to some extent. And today, the way that, because CO2 costs something to the operators, they re-inject it over and over again as much as possible in order to use it and maximize it. But imagine if there were policies in place that were, you know, requesting that more carbon be stored in the earth than the carbon equivalent of the oil out. And because again, there's depleted oil and gas pore spaces in the earth, not to mention there's, it's called stacked storage. So in this example here, you see where the green is, where there could be oil and gas, but then there's also pores in the rock itself that might only have water. One thing that, from just a physical chemistry perspective, the carbon atom density of supercritical CO2 will never be greater than the carbon atom density of oil. So for one, you're not going to be able to put more carbon in the earth than oil you get out. The operators would have to put more carbon in the earth by putting it in different pores, not like the in-place oil that they're getting out. You don't get a 1-for-1. So there would have to be an incentive to put more carbon in the earth than the carbon equivalent of the oil coming out, all the way into the internal combustion engine. We are far from that today. It doesn't mean we can't get there. Of all of the utilization, 60 million tons of the CO2 is really naturally sourced from the earth today for EOR. So most of it is naturally sourced, not anthropogenic. So the first step is like, stop doing that and really just use anthropogenic CO2, of which there's plenty around. And then of course, if you use CO2 from direct air capture, you have the potential of having for sure neutral and maybe even negative fuel. In these last couple of slides, I'll just leave you here. This is a study that you can take a look at. It was spearheaded by Roger Ains at Lawrence Livermore National Labs, and it had to do with the state of California and their carbon neutral plan by 2045, in which direct air capture played a role. And that's chapter 5, and my group authored that. And again, we looked at pairing up to geothermal and waste heat in the state of California to really achieve the lowest costs of doing this and moving it forward. And we're at thousands of tons removal today, and we were, you know, this could potentially get us to that millions of tons as the next step. So I'll end just by saying that, you know, the new portfolio, of course, it includes first and foremost deep decarbonization, but now must also include direct removal of CO2 from the atmosphere. And here's a bunch of links to more information on everything. And I'm happy to answer questions in the remaining time.
Amazing. Thank you so, so much, Jen. This was awesome for me. I have a lot of my own questions, but I am going to go ahead and just dive in with some of the questions that we've gotten from the group today. So from Andrew, and I don't know if we want to actually put this chart back up on the screen, but I think he's referencing the one where you're looking at the concentrations and purity levels for extraction. He said, awesome chart. I'd love to know how far existing DAC technologies are from the theoretical minimum work, and therefore what the theoretical headroom is for gains from where we sit today.
Yeah, so there's a separate study. So Andrew, you can send me an email and I'll follow up with a paper that we wrote on this back in 2011. Here was that, maybe it was 2014, but anyway, it was looking at something called the second law of efficiency and how that changes with the concentration. And so the second law of efficiency is exactly what you're talking about. In other words, you have the real work, which is always going to be higher than the minimum work. And so the higher the efficiency, the closer those values are, okay? The second law of efficiency. And we found that for direct air capture in that study, they're pretty low, the efficiencies. In our National Academy of Sciences report, we did it more rigorously for the solvents and solid sorbent-based cases. And the second law efficiencies were somewhere around, say, 6% or something like that, pretty low. Where the more concentrated streams, it might be like 10 to 15%, you know? So what we did find in that older paper is that that second law of efficiency, you get closer and closer to the minimum work as your concentrations increase. The qualitative reasoning for that is that, and I have a picture somewhere of this, but imagine that, you have a box and 400 parts per million in that box is CO2, and that's what you want to separate. Now you multiply that 400 parts per million by 300, and those are the parts now that you want to separate. The problem is you don't just get to go and choose, the CO2 molecules that you're after. You have to touch everything. You have to touch all of the inert stuff too. So you got to process the nitrogen, the oxygen, the water vapor, and the CO2. So it's almost like, you multiply that CO2 by 300. Now all the particles that you touch, you're more likely to touch the ones that you're interested in. And it's just, that's the efficiency argument. You just have more stuff, it's easier to separate. And in your processing, less inerts, the more concentrated you have. And so, and that's really the second law, and so how much room do we have? If you believe that correlation, I think there's absolutely still some room. And, but that's in part why it's important to kind of look at, I didn't show it today, but like the energy breakdown too, like understanding where are the entropy losses in the system. There's a new technology out, I think the company's called Wilcox, and it's not based upon, these are very thermally driven processes, and they are electricity driven. And so it's like they are able to, instead of regenerating thermally, they can regenerate with electricity. And it's just one type of energy going into their system. There's other limitations, but I think that kind of an approach is interesting. And those kinds of approaches, the fewer the process unit operations that you have, the fewer number of process steps you have, the more efficiency that you're going to have in the end. And so that's an elegant process, for instance, if that helps.
Sorry, my dog is barking in the background.
Yeah.
Yeah, as happens sometimes. So I'm sorry for the background noise, everyone. Kind of following from that, and in terms of like unit operations and efficiency, James Lavin had a question about the solid sorbent process, asking about air resistance and pore size. So, thinking about increases in air resistance as it relates to pore size and solid sorbents. And he's wondering how much energy is needed to drive fans as a % of the overall energy requirement of the solid sorbent system.
Yeah, so I'm trying to visualize this plot that I made before, where I actually show the breakdown of the fan versus the thermals versus like all of the parts. The largest piece by far is the thermal component of the energy. My guess is, and I have to go back, but like the fan power is probably like 5 to 10% or something like that. But it's optimized, so the fan power is something that is can be reduced by shortening the pressure drop. So if you don't have to move your air through as long of a pathway, then you can reduce that demand, that energy demand there. But the channel sizes of the monoliths are also tuned for for this as well. So like the catalytic converter, and the honeycomb structure, the sizes are of those millimeter sizes of the channels through that honeycomb structure has been optimized for the automobile. And so this same type of structure is optimized for the direct air capture contactors, either Climeworks or Global Thermostat. I mean, that's work that they're doing that's probably proprietary, that's internal to their systems. That those, it's probably on the order of millimeters, but that's something that they have optimized in order to minimize fan power for achieving minimal pressure drop across their materials. But then there's another piece that's important. it's not just pushing the air through, it's also something called residence time. It's about allowing the air to have enough time in the monolith so that the CO2 can diffuse from the inside of the channel all through maybe a tortuous pathway. Like if, let's say that we were to make this stuff with activated carbon, which is pretty cheap and easy to make today, and you chemically functionalize activated carbon with amines, that's pretty cheap. The issues with activated carbon is that the pathway for the CO2 is very tortuous. Whereas we have these slick designer materials like metal organic frameworks, and you can make these long channels, like, so like on the, you know, on the nanometer scale, it's like the CO2 is saying, wow, what a free path I have, right? There's like very minimal diffusion resistance. And so now it's able to actually get to the chemistry. It's not the reaction of CO2 in the nitrogen on the amine that's the limiting step. It's not the reaction committed, it's diffusion. And that's going to dictate the throughput of your system, you know? So all of that stuff gets optimized. And that's why, again, we need more companies, more human capital, more people just getting excited about this kind of work, because there's a lot to do.
Yeah, I mean, that's amazing. I think that follows pretty nicely into the next sort of, I'm going to kind of group these questions in together. So Andrew, you know, says maybe a basic question. I love basic questions. Would love to hear your point of view on some newer sorbent technologies. So expanding a little bit on MOFs. And also Adnan asked, you know, it says he's interested in how far we are in converting gaseous carbon dioxide straight to a solid usable form. So basically, I think what we're getting at is new sorbent technologies, and then kind of coupling that to, you know, what strides in your point of view, or what are you excited about in terms of maybe integrating some reactive capture technologies into direct air capture?
Sure. So there's really two chemistries. You know, the chemistries are either carbonates, so like oxygen with CO2, and then there's carbamates or carbamates, which is nitrogen and CO2. So good news is you don't have a lot of options right there. But then the question is, you know, what kind of substrate are you going to put it on? And that's what's going to affect really the diffusion in terms of solid sorbents. Again, we talked a little bit about the solvents already, and it's a strong base because you just don't have that same kind of interaction potential that you have with these really high surface area materials. So we can get away with weak bases. And there's a ton of different types of, you know, when I say there's two options, carbonate and carbamate, there's a lot of options of what kind of nitrogen functionality one can have out there, like lots of different types of amines. There's lots of different types of, you know, ways to get oxygen to react with CO2 as well. And in some cases, it's a little of both. You know, you often have water vapor around, and the water can interact with the surface and then also interact with CO2 to form. So you have mixtures of carbamate and carbonates as well in systems. And so part of it is the chemistry. And then, but I think the more exciting and interesting part isn't the chemistry, but it's more of the architecture. It's more of the structure and trying to minimize the diffusion resistance of CO2 to arriving at the chemistry in a timely way. And that's why I think metal organic frameworks are interesting, because they have these huge, large channels. But it doesn't mean we can't do that with other materials. You know, there are carbon-based materials that you can do that with too. And I think that it's going to be a portfolio of chemistries, a portfolio of companies. You know, if you have a headache and you go to the pharmacy, how many options do you have? You have a lot, right? And so I think that, I hope that it's just going to be a lot of fun competition of just people getting into this and doing it, because we need it all, you know. But that's those kinds of chemistries, and really looking at thermal regeneration. But there's also ways where you can, you know, pass an electric current through in order to, you know, break a bond as well. And so I think that that's another technology that's interesting. That's a different approach, because there's one thing about the diffusion resistance, and that's more material science engineering and chemistry. But then the other piece, which is chemical engineering and process engineering.
Mm-hmm.
And that is, you know, more of a systems based. It's a total system of, like, for the thermal, it's like, well, how are we going to get the heat there fast? Because that's not just about getting the CO2 to the chemistry, but how is the heat moving through the system? Because the faster we can get the heat to move through the system, the faster those bonds break, and the faster we produce the high purity CO2, and the smaller the capex is, because our throughput's higher. So heat transfer is super important in materials that have good heat transfer. But then going back to process, the electrical swing materials to me are interesting, because if we want to use low carbon energy, you know, a large challenge in deep decarbonization in the United States is trying to figure out how to get low carbon heat, right? This is hard. We have such a dependence on natural gas, and which is fine, but it's not carbon free, right? And so it's, you know, low carbon heat is not straightforward. It's doable, but it's not straightforward. You know, you have to think about electric heating, so that at least you can use renewables to do that. You have to think about maybe heating with hydrogen, but how do you get the hydrogen? And so it's tricky, right? So electric swing to me is interesting because it directly couples to photovoltaics. It directly couples to, you know, to wind or hydro, or, you know, other low carbon. The other part you talked about is CO2 to solids. Now, to me, that sounds a lot like CO2 mineralization, and I think that there's a lot of potential in that field, but you have to ask yourself, where's the alkalinity coming from? So there's only so much cheap alkalinity. Cheap means it's got a lot of magnesium or calcium, you know, and which is kind of the heart of the alkalinity to be reactive to CO2 to form like magnesium carbonate or calcium carbonate. And then, and so you need materials that have that, but they also need to be reactive, which typically means you need them to be like less than 100 microns in particle size. And so if you ask yourself where all that is, the answer is mine tailings. The answer is industrial byproducts. And so, you know, mine tailings, if you look at, say, there's mining opportunities out there where you're interested maybe in mining diamonds and platinum and palladium and nickel, which is only going to increase with battery increase. But like with these kinds of materials, it turns out that magnesium and calcium is highly correlated with them in the Earth's crust. And so it turns out that the tailings themselves have alkalinity associated with them, and they're a waste process from those mining industries. And there's literally piles of this stuff. We have 2 projects in my group where we're working with 2 different mines and looking at the reactivity and trying to enhance the reactivity of their alkaline wastes. And so that kind of work is very interesting. I find it exciting because in the end, you form an aggregate, like a carbonate or, you know, these kinds of materials that can be used as a feedstock for construction. Mm-hmm. And they could potentially replace, you know, sand and gravel, which is often those sourced locally, you know, for building. Yeah. So some of the work we're doing is trying to look at, well, where are there shortages in aggregate production or mining in the US, and how much potential does synthetic aggregates, how much potential could they play in, because when you take CO2 from air and you ask yourself, what do you do with it? If you convert it to a fuel, good news is you get, that has a value, right? It's not negative emissions, but it has a value. Mm-hmm. If you do EOR, that barrel of oil that you produce in the end has a value. If you have dedicated storage, what do you get? You get the satisfaction of getting rid of it, right? And maybe some federal tax credits from 45Q. But to me, it's like, well, I mean, at least you have value if you make a synthetic aggregate. And if there's a way that you can make it stronger, if there's a way that you can upcycle and you make a product that is more valuable than sand and gravel, then that could be interesting. And it's just another path.
Amazing. given us a lot to think about. There are so many more questions, including mine, but we are unfortunately out of time. So I think what we're going to do is pull the chat log. And if you don't mind, we can forward some of the additional questions to you.
No problem.
Okay. And then we'll also there are some folks in the Zoom chat group sourcing answers, which is also really great. There's a really great discussion going on there. So I just want to, I want to thank you so much for taking the time to speak to us today. I know I learned a lot. I cannot wait to dig into this technology more and learn more about it. And yeah, I don't know if we do applause on Zoom calls, but you know, snaps, thank you so much for being here.
Yeah.
And I think we're gonna have some breakout sessions next. I'm going to pass it back over to Jason, who is going to help us wrap things up. And thank you so much, Jen. This was
Thanks,
amazing.
you guys. Thank you.
Thanks, Kristen, and especially thank you, Jen. This was a remarkable talk. I'm looking forward to learning more about the technology, and I'm especially looking forward to going back through the recording of this that we, by the way, will circulate afterwards, so that we can parse out some of the just remarkable insights that came from this.
And Jason,
discussion.
feel free to post the slides. It's all public, so if that's useful to anybody.
Yes, we can post it. We'll post the slides as well. So great. Excellent. Great. So
I'm going to sign off, but thanks, you guys. Take care. Have a great day.
Thank you, Jen. Thank you.